On March 28, 2026, at 4:15 UTC, a routine overnight data stream from the James Webb Space Telescope turned into something far less routine. 8 hours earlier, the telescope's near-infrared camera, operating in wide-field slitless spectroscopy mode from its position at the Sun-Earth Lagrange point 2, roughly 1.5 million kilometers from Earth, had captured a spectral absorption profile from the coma of the interstellar object known as 3I, Atlas. What made this observation unusual was not just the data itself, but how it was flagged. The instrument's automated anomaly detection pipeline assigned the signal its highest priority classification, labeled Q, before any human scientist had reviewed it. During the overnight processing shift at the Space Telescope Science Institute in Baltimore, the duty scientist retrieved the flagged file at 4:15 UTC and began examining the data. The focus quickly narrowed to a distinct absorption line at 670.2 nanometers. To verify its significance, she cross-referenced the signal against the molecular spectral database maintained by the NASA Astrobiology Institute. What followed was an extended pause, lasting 11 minutes. Not because the data was unclear, but because it was unmistakably clear. In molecular spectroscopy, an absorption line at that precise wavelength corresponds to a single known molecular structure. There was no ambiguity, no alternative interpretation, and no competing identification. Recognizing the importance of the finding, she bypassed the standard reporting queue and contacted her section chief directly at 4:26 UTC. The response was immediate. The section chief arrived at the institute within the hour, and by 6 UTC, the raw telemetry had already been forwarded to multiple independent research bodies, including NASA's Jet Propulsion Laboratory Astrobiology Rapid Response Team, the European Space Agency's Science Operations Center, and the Atacama Large Millimeter, Submillimeter Array in Chile for cross-verification across different observational platforms. By 7:30 UTC, the European Space Agency took the unprecedented step of temporarily removing its public Gaia spectral database from access, describing the action as an emergency recalibration in an official statement. In the history of coordinated international astronomy spanning 4 decades, there had never been a simultaneous multi-agency data restriction of this magnitude, triggered by a spectral detection. The reason for this extraordinary response became clear when the data was fully analyzed. At 4:15 UTC on March 27, 2026, 3I, Atlas exhibited a spectral signature corresponding precisely to chlorophyll-A, a magnesium-centered porphyrin complex that forms the core of photosynthetic systems on Earth. The detection indicated a concentration of approximately 4.22 parts per million across the object's coma, with a measured temperature of -240 degrees Celsius. What made the observation particularly significant was that the signal was independently confirmed across multiple instruments, including JWST's near-infrared camera, ESA's Gaia photometric instruments, and ALMA's millimeter wave array in Chile, each operating at different wavelength regimes. The combined confidence level of these independent confirmations reached 99.8%. At this stage, the scientific conclusion was carefully restrained. The object itself was not declared alive, and the data did not allow for such a determination. However, the measurements did provide a clear and unambiguous molecular identification. The compound detected possesses a highly specific 7,2 atom structure, one whose formation pathways, stability requirements, and functional configuration are not consistent with known abiotic processes. Across all documented environments within the solar system and interstellar medium, no natural mechanism has been observed that produces such a molecule in intact form under those conditions. Understanding why this identification carries such weight requires a closer examination of the molecular structure itself, along with the spectroscopic characteristics that define it. Chlorophyll A is not a simple organic compound. It is a chlorine derivative built around a central magnesium ion, coordinated within a tetrapyrrole ring structure. This ring is composed of 4 interconnected subunits linked through methane bridges, forming a conjugated system that enables its unique light-absorbing properties. Attached to this core is a hydrophobic phytyl tail, which anchors the molecule within biological membranes. The significance of this structure lies in its complexity and precision. The arrangement of its 137 atoms is not arbitrary. It is responsible for the molecule's quantum mechanical behavior, including its ability to convert absorbed photon energy into chemical energy with remarkable efficiency. In photosynthetic organisms, this process operates with an efficiency approaching 95%, a phenomenon that was not fully understood until experimental work in quantum biology demonstrated coherent energy transfer within the system. These findings, published in the early 21st century, showed that energy absorbed by chlorophyll is transferred through quantum coherence pathways rather than purely classical mechanisms. Chlorophyll A's absorption spectrum is also highly specific, with peaks near 430 nanometers in the blue region and 670 nanometers in the red region of visible light. These wavelengths correspond to resonant interactions between incoming photons and the molecule's delocalized pi electron system within the porphyrin ring. This resonance is not a general property of organic molecules. It requires the exact geometric and electronic structure of the intact tetrapyrrole configuration. Any partial or degraded version of the molecule produces a different spectral profile. The 670.2 nanometer absorption line detected in the coma of 3I Atlas matches this profile with precision. It is not a nearby approximation, nor a related compound, nor a precursor molecule. Combined with the secondary absorption feature at 430 nanometers, confirmed by ALMA, and the consistency of the spectral signature across multiple instruments, the data identifies the presence of the complete chlorophyll, a molecule in its intact form. The implication of detecting intact chlorophyll A in an interstellar environment extends far beyond simple molecular identification, because the conditions required for such a molecule to remain stable are extremely restrictive. Chlorophyll A is not only structurally complex, but also chemically fragile when exposed to the harsh realities of space. Its integrity depends on the preservation of its porphyrin ring system, particularly the delocalized pi electron network that gives the molecule its characteristic absorption properties. Any disruption to this structure alters its spectral signature, meaning that the precise 670 2 nanometer absorption line observed in the coma of 3I Atlas corresponds to an undisturbed, fully functional molecule rather than a degraded fragment or related compound. To understand why this matters, it is necessary to consider how such molecules behave outside controlled environments. In terrestrial conditions, chlorophyll A is maintained within biological systems where it is continuously protected, repaired, and stabilized by cellular structures. Outside of those systems, exposure to ultraviolet radiation, ionizing particles, and reactive chemical environments quickly leads to decomposition. In interstellar space, these destructive influences are not only present but amplified over time. Cosmic rays, consisting of high-energy protons and atomic nuclei accelerated by astrophysical processes such as supernovae, interact with molecular structures through direct collisions and secondary particle cascades. These interactions break chemical bonds, particularly carbon-nitrogen and carbon-carbon bonds, which are fundamental to the integrity of porphyrin-based compounds. Over timescales measured in millions of years, such radiation would be expected to reduce complex organic molecules to simpler fragments. This process, known as radiolytic degradation, is not selective. It affects all large, structured organic compounds lacking protective shielding. Given the estimated duration of interstellar travel for 3I, Atlas, any chlorophyll-like molecule present at the beginning of its journey would be expected to undergo significant structural breakdown long before reaching the inner solar system. The detection of an intact molecule under these circumstances is therefore not merely unusual, it contradicts established expectations based on known physical processes. The spectral data itself supports this conclusion. The absorption line at 670.2 nanometers shows no measurable broadening, no frequency shift, and no reduction in intensity that would indicate partial degradation or structural modification. In spectroscopy, line broadening can occur due to a range of factors, including thermal motion, molecular collisions, or perturbations in the surrounding environment. Similarly, shifts in absorption frequency can indicate changes in molecular structure or interactions with other compounds. The absence of these effects in the observed data suggests that the molecular population responsible for the signal is both homogeneous and structurally intact. Cross-validation from multiple instruments strengthens this interpretation. The Atacama Large Millimeter, Sub-Millimeter Array provided complementary observations at longer wavelengths, confirming not only the primary absorption feature, but also a secondary feature at approximately 430 nanometers, which corresponds to another known absorption peak of chlorophyll-A. The consistency between these independent measurements, taken from different observational platforms and operating across distinct wavelength regimes, reduces the likelihood of instrumental error or misidentification. Each system operates under different calibration frameworks and detection principles, yet all converge on the same molecular identification with a high degree of confidence. At this point, the discussion shifts from detection to plausibility. In astrochemistry, the formation of complex organic molecules is well documented in certain environments, particularly within molecular clouds, cometary ices, and protoplanetary disks. However, these processes typically produce simpler organic compounds or incomplete precursors rather than fully assembled, functionally active biomolecules. The formation of a complete porphyrin ring structure, especially one coordinated with a central magnesium ion and attached to a phytyl tail, requires a sequence of reactions that are highly specific and typically dependent on biological or highly controlled synthetic pathways. In laboratory settings, the synthesis of chlorophyll-A involves carefully regulated steps that guide the assembly of the tetrapyrrole ring, insertion of the magnesium ion, and attachment of the hydrophobic tail. These steps occur under conditions that provide controlled temperatures, specific reactants, and catalytic environments. In contrast, the interstellar medium is characterized by extremely low temperatures, low particle densities, and a radiation environment dominated by high-energy particles. While such conditions can support the formation of simple organic molecules, they do not naturally facilitate the assembly of large, structurally precise biomolecules with the functional complexity of chlorophyll-A. This distinction is critical when interpreting the detection. The presence of the molecule is not simply a matter of identifying carbon-based chemistry. It is about recognizing a specific arrangement of atoms that achieves a precise functional outcome. The porphyrin ring's ability to absorb photons at specific wavelengths depends on its conjugated electron system, which in turn depends on the integrity of its geometric structure. Any deviation from that structure results in a different spectral signature. The match observed at 670.2 nanometers, along with the supporting absorption features and high-confidence cross-instrument agreement, indicates that the molecule is not only present, but retains the configuration necessary for its characteristic function. At the same time, the surrounding environment of 3I, Atlas, adds another layer of complexity. The object's coma, composed of gas and dust released from its surface as it approaches the Sun, provides a medium in which molecules can be detected spectroscopically. However, this environment is also subject to solar radiation, particle interactions, and thermal variations. The persistence of a fragile molecule, like chlorophyll-A, within this environment suggests that it is either being continuously replenished, actively maintained, or protected in a way that prevents degradation. The spectral data alone does not distinguish between these possibilities, but it does establish that the molecule is present in a form consistent with laboratory-grade integrity rather than partially degraded remnants. Building on the confirmed identification of intact chlorophyll-A, the next layer of analysis focuses on the environmental conditions required for such a molecule to not only exist but remain detectable with the clarity observed. The data does not merely show the presence of a complex organic compound, it shows that the molecule retains its full structural and functional characteristics in a setting that, under normal physical expectations, should be hostile to its preservation. One of the most significant aspects of the observation is the thermal profile associated with 3I Atlas. Independent measurements from instruments, such as NASA's Deep Space Network Antenna, DSS 43 inches Canberra, combined with observations from ALMA, revealed a departure from the expected equilibrium temperature of the object. Based on its heliocentric distance and assumed low albedo, the expected temperature of the coma should be approximately -240 degrees Celsius, a value consistent with passive heating and radiative balance in deep space. However, the thermal mapping showed something unexpected. Instead of a uniform temperature distribution, localized regions within the coma exhibited temperatures reaching approximately +15 degrees Celsius. These warmer regions were not randomly distributed. They appeared in discrete zones that spatially correspond to the areas where chlorophyll-A concentrations were highest, as later confirmed through spectroscopic analysis. This spatial correlation between molecular detection and thermal anomaly is a key feature of the dataset. From a physical standpoint, maintaining a temperature significantly above the ambient equilibrium in a vacuum environment requires a continuous energy source. In space, there is no atmosphere to retain heat, and any localized thermal energy will radiate away unless it is actively replenished. Geological processes such as radioactive decay can produce internal heat in planetary bodies, but this heat is typically distributed gradually through conduction and results in broad, diffuse temperature gradients rather than sharply defined hotspots. The thermal anomalies observed in 3I Atlas do not match this pattern. Instead, they appear as isolated, stable regions of elevated temperature. The magnitude of the temperature difference is also important. A shift from -240 degrees Celsius to +15 degrees Celsius represents a difference of over 250 degrees. This is not a minor fluctuation. It is a substantial deviation that places the affected regions within a temperature range where liquid water can exist under appropriate pressure conditions. While the coma itself is a low-density environment, the significance lies in the fact that the detected temperature aligns with the lower boundary of the liquid water phase under standard pressure conditions. This temperature range is particularly relevant when considering the functional properties of chlorophyll-A. In terrestrial systems, the molecule operates within environments where water is present in liquid form, allowing for the molecular interactions necessary for energy transfer processes. The quantum efficiency of chlorophyll-based systems depends on a stable molecular configuration, which in turn is supported by specific thermal conditions. The coincidence between the observed thermal anomalies and the regions of chlorophyll concentration raises questions about whether the thermal environment is being maintained in a way that supports molecular stability. The data further indicates that these thermal regions are not transient. The observations from DSS 43 and ALMA suggest that the elevated temperatures are sustained over time rather than representing brief or isolated spikes. Sustained thermal equilibrium in a vacuum requires continuous energy input that counteracts radiative cooling. Without such input, any localized heat would dissipate rapidly into surrounding space. The persistence of these hotspots implies the presence of a mechanism that actively regulates temperature in specific regions. Another notable observation is the alignment between the thermal anomalies and the spatial distribution of the detected molecular signatures. The regions exhibiting elevated temperatures are not offset from the chlorophyll-A signals. Instead, they overlap. This spatial correspondence suggests a relationship between the presence of the molecule and the conditions being maintained in its immediate environment. While correlation alone does not establish causation, the consistency of this pattern across multiple observation methods strengthens the case that the two phenomena are linked in some way. From a thermodynamic perspective, passive processes such as solar heating are insufficient to explain the localized nature of the anomalies. At the distance of 3i Atlas from the Sun, solar irradiance is relatively weak and would produce a gradual and uniform heating effect rather than discrete hotspots. The observed distribution does not match this expectation. Instead, it suggests that energy is being applied selectively to specific regions, maintaining temperatures that differ significantly from the surrounding environment. At this stage, the analysis remains cautious in its interpretation. The data describes what is observed, not what is responsible for it. However, the combination of intact molecular detection and localized thermal regulation introduces a level of complexity that goes beyond simple passive physical processes. The presence of chlorophyll-A, coupled with sustained temperature control in its immediate vicinity, suggests that the system is not in a purely inert state. Whether this reflects an unknown natural mechanism or a more structured process remains undetermined, but the observational evidence clearly indicates that the conditions within the coma are not uniform and not entirely governed by equilibrium alone. As additional data continues to be processed and cross-referenced across multiple observatories, the focus shifts toward understanding how these distinct phenomena, molecular integrity and thermal regulation, interact within the same spatial framework. The alignment between them is not incidental in the dataset, and it forms the basis for deeper investigation into the underlying mechanisms that could produce such a configuration in an interstellar object traveling through the solar system. As the analysis progressed, attention shifted from the existence of chlorophyll-A and localized thermal anomalies to how these observations evolved over time as 3I Atlas moved along its trajectory. Temporal changes in spectral intensity provided additional insight into the behavior of the system, revealing patterns that could not be explained by static or passive conditions alone. On March 25, 2026, at approximately 14:33 UTC, NASA's Deep Space Network Antenna DSS, 43 inches Canberra, recorded an unexpected shift in the thermal emission profile of 3I Atlas. Based on predictive models, the object's temperature, determined by its distance from the Sun and assumed low reflectivity, should have remained relatively stable at around -240 degrees Celsius. However, the measurements indicated the presence of localized regions exhibiting temperatures significantly higher than expected, reaching up to +15 degrees Celsius. These thermal anomalies were not uniform across the object. Instead, they appeared in discrete, spatially confined areas distributed across the coma. Subsequent analysis showed that these same regions corresponded to the zones where chlorophyll-A concentrations were later detected. This overlap between thermal activity and molecular presence became one of the central features of the dataset, as it suggested a non-random association between energy distribution and chemical composition. The temporal aspect of the observations added another dimension to the analysis. As 3I Atlas approached closer to the Sun, crossing the projected orbital boundary of Jupiter's gravitational influence. The intensity of the chlorophyll, a spectral signal, increased significantly. Over a 4-hour observation window on March 25, the emission intensity associated with the molecule rose by approximately 314%. In spectroscopic terms, such an increase can be influenced by either a rise in molecular concentration, an increase in excitation energy, or a combination of both. In passive systems, particularly those involving inert or frozen material, such a rapid and substantial increase in spectral intensity would not be expected. Molecular concentration in a static environment typically changes slowly, governed by processes such as sublimation, outgassing, or chemical reactions, none of which would normally produce a threefold increase in such a short time frame without an external driving force. Similarly, in the absence of an energy source, excitation levels would remain relatively constant or decline rather than increase. The observed increase suggests that either additional chlorophyll, molecules were being introduced into the coma, or that existing molecules were receiving increased energy input that enhanced their spectral response. Both scenarios imply active processes rather than purely passive ones. The data alone does not distinguish between these possibilities, but it does indicate that the system is not static and that changes are occurring on relatively short timescales. Further observations added another layer of complexity. At approximately 2:15 UTC on March 27, the Hubble Space Telescope's Wide Field Camera 3 detected a secondary spectral feature corresponding to chlorophyll B. On Earth, chlorophyll B functions as an accessory pigment that complements chlorophyll A by expanding the range of light wavelengths that can be absorbed. Specifically, it captures light in the blue-green region of the spectrum, around 480 nanometers, and transfers the absorbed energy to chlorophyll A through resonance energy transfer mechanisms. The presence of chlorophyll B alongside chlorophyll A is not typically independent in natural systems. In biological organisms, the two molecules operate as part of an integrated light harvesting system, with chlorophyll B extending the absorption spectrum and increasing the overall efficiency of photon capture. Its detection in the coma of 3I, Atlas therefore does not represent an isolated finding, but rather the presence of a complementary component that, in terrestrial systems, serves a specific functional role alongside chlorophyll A. The coexistence of both pigments raises important considerations about the nature of the system being observed. Chlorophyll B does not function in isolation. It is part of a coordinated arrangement that depends on the presence of chlorophyll A. Its role is not redundant but supportive, enhancing the range of wavelengths that can be utilized within the same energy conversion framework. The detection of both molecules in the same spatial regions suggests that they are not randomly distributed, but instead share a common context within the coma. At the same time, the ALMA cross-reference data introduced an additional spectral component associated with metallic elements. Specifically, the analysis identified the presence of unoxidized titanium and molybdenum isotopes within the same spatial zones as the chlorophyll detections. These elements, when observed in natural environments, are typically found in oxidized forms due to their high reactivity with oxygen-bearing compounds. The detection of unoxidized metallic states in an oxygen-rich coma environment is therefore noteworthy. The spatial correlation between the metallic signatures and the chlorophyll molecules suggests that they are not independent features of the environment. Instead, they appear to coexist within the same structural framework, indicating a potential relationship between the chemical and physical components of the system. The presence of these metals in reduced form implies conditions that either prevent oxidation or actively maintain a reducing environment in localized regions.